Greetings, dear students! This video is part of the course Testing of Liquid Propellant Rocket Engines from the Department of Aircraft Engine Theory at Samara University. In this course, you will learn why tests are conducted, how to organize them, what tools are needed to conduct them successfully and safely, how to process experimental results to get the most accurate information, how to get the desired result with a minimum number of tests, and much more. The subject of this course is the Liquid Propellant Rocket Engine, which is an engine that runs on liquid fuel components on board an aircraft. The fuel components are oxidizer and propellant. The most important advantage of such engines is that they do not use atmospheric air as an oxidizer. This feature allows the engine to operate in airless environment, in space, underwater, etc., and develop the necessary thrust. LPREs are designed to provide short-term thrust. It ranges in magnitude from fractions of a newton to 1,000 of kilonewtons. This is the first video, the first part of the course. In it, I will tell you what kind of tests are carried out on liquid propellant rocket engines and their components, why they are carried out, and what tasks are solved. We begin, of course, with a definition. Testing is the experimental determination of its quantitative and qualitative properties of the test object as a result of various factors arising from its operation. In the case of a liquid propellant rocket engine, the main purpose of testing is to assess the performance of the engine's technical systems and to investigate the processes that occur in the engine. During the LPRE testing, the following major tasks are solved. Obtaining real hydraulic power and strength characteristics of the engine under different conditions. Finding the best design and construction solutions. Studying the interaction of engine components during operation. Quantifying engine reliability. Determining the influence of external factors on the engine operation. Determining the limits of the engine's performance capability. Engine operating techniques. It is well known that many complex technical devices, such as gas turbine and other thermal engines, are tested. However, the working process of a liquid rocket engine has its own features, which affect the testing process. Let's take a brief look at the main features of LPRE testing. The short operating time. The operation of a rocket engine on a single startup typically lasts from a few seconds to a few minutes. And during this time, the engine is started. Several modes of operation in terms of combustion chamber pressure and K-fuel ratio and other tests are performed. The short operating time excludes the possibility of analyzing and correcting the cause of the test while it is in progress. Therefore, tests must be as automated as possible, and the measuring instruments used must be fast but also have a high degree of accuracy. This requirement is not always met, and for a single parameter, sometimes two measuring instruments are used to measure rapidly and slowly changing variables. High testing and environmental risks. The reason for this is the use of highly reactive fuels and oxidizers, such as liquid oxygen, fluorine, and nitric acid components. Their use causes high temperatures in the combustion chamber and a rapid development of defects which can lead to an explosion. In addition, some rocket fuels are highly toxic, for example hydrazine and its compounds, and tend to explode under various influences, hydrogen peroxide. The danger increases with high thrusts. During tests, the possibility of an explosion, the power of which may exceed the engine's capacity, cannot be avoided. High cost. Testing requires a test station, a special set of equipment that requires highly trained staff, a means of simulating real conditions, reliable protection of people and equipment, and the supply of disposal of enormous energies. High reliability requirements. The special nature of the LPRE application in launch vehicles and space objects lead to very high requirements for their reliability. These requirements define the test program over the entire range of possible combinations of internal and external factors. External factors include pressure and temperature of fuel components at the pump inlet or engine inlet, turning angles of thrust regulator actuators and component ratios, and internal factors include variation in size of constructions and hydraulic characteristics of throttles, lines, and gas paths. This, in turn, makes it necessary to simulate all possible conditions during tests, which of course increases their time and cost, and also expands the range of equipment required. Many types of LPRE tests depending on their purpose. The many types of LPRE testing are related to different purposes of the engines themselves and to their operating conditions. Also, as noted earlier, it is necessary to simulate different effects on the engine. LPREs can be used both in the main propulsion systems of aircraft, cruise LPREs, and in control and altitude control system as actuators, low-thrust liquid rocket engines. Naturally, the operating conditions and requirements for these LPREs differ significantly, so do the test methods and equipment used. In this regard, test planning methods that will provide more complete engine data in a shorter time, and therefore at minimum cost and risk, play a high role. Also, in order to obtain comprehensive information about the processes taking place, the engine must be dissected as much as possible in order to gather the most complete information. For example, 575 parameters were measured during a test of an American LPRE. The LPRE tests are usually multifactorial, meaning they take into account the influence of many factors. Tests are conducted in large numbers to accurately assess the reliability of a liquid rocket engine. Sometimes it is necessary to conduct tests in boosted and loaded modes, which are characterized by increased, compared to nominal mode, component flow rates, extreme or above gas saturation values, a wide range of inlet pressures and other external conditions. The following requirements are generally applicable to the LPRE tests. Testing and measurements must be automated. The obtained results should be as informative as possible. Tests should produce more complete data on the engine in the shortest time and the lowest construction cost. All necessary parameters should be measured during the test with high reliability and accuracy. The measurements should be duplicated. Measurements and recording of results must be carried out for the duration of the tests. The tests must be reliable and safe both for the staff and equipment and for the environment. In different stages of their life cycle, testing deals with different tasks. First, at the preliminary research and design stage, following tasks are solved. Building a scientific and technical foundation. assessment of the degree of design excellence and identification of design errors, comparison of design variants and selection of the best one of them, refinement and development of experimental and prototype samples to specified requirements. Second, at the production stage of units and the engine in general, following tasks are solved: assessment of the quality level of the product, assessment of the technical level of the manufactured products, checking the technological level of the series production process, control of key parameters during series production. Third, at the operational stage of LPRE, these tasks are solved: determination of the actual values of the LPRE performance parameters under real-world conditions, making recommendations to improve efficiency and sustainability of quality indicators, making operational recommendations, making recommendations to improve the product based on the results of the operation. This slide shows possible tests that can be carried out in the experimental development of an engine during its construction and in checking the quality and reliability of the engine during production and operation. These types of tests, their purpose and features will be described in detail on the following slides. LPRE tests and their components can be classified in a variety of ways. First, by the presence of the combustion reaction or decomposition of engine fuel components. All tests of LPRE, as well as their individual components and systems, are categorized into fire and cold tests. Second, they can be classified by location as ground and flight. Third, depending on the stage of the engine's life cycle, testing of LPRE is divided into research, experimental, and operational. Fourth, according to the tested construction, the tests can be divided into tests of the complete engine and autonomous tests of engine parts and units. A liquid rocket engine is a complex system consisting of individual assemblies, units, systems, and their components. Therefore, the development of LPRE structure, in general, or the testing of an assembled LPRE, may be preceded by a test cycle of individual units or assemblies, or their systems, to determine their characteristics. Autonomous tests can be cold and fire tests. All cold tests are autonomous in nature. Fire autonomous testing involves combustion chambers and gas generators of LPRE. Most of the assemblies and units of LPRE operate under conditions not directly related to the fuel combustion process. This applies primarily to elements of the feeding, control and regulation systems of the LPRE. The testing of these components can be carried out to a large extent under laboratory conditions by means of autonomous cold tests. Conducting cold tests allows to reduce the amount of testing of full-size engines, which significantly reduces the cost and time of testing new LPRE, makes the process of development and quality control of engine components more secure, allows in many cases the replacement of the unique test equipment with simpler and more reliable ones, allows the change of operating modes of components within a wider range than possible on the engine. The above-mentioned features of cold tests were the reason for their widespread implementation in the development of new liquid rocket engines and in the control of serial production. The disadvantage of these tests is the difficulty in reproducing the same operating conditions as a full-size engine. The main types of cold tests can include hydraulic spills of pipes, valves, regulators, nozzles, cooling ducts, combustion chambers, and gas generators, etc., allowing to determine the actual resistance of individual structural elements and take into account, when calculating engine setting parameters, to evaluate the uniformity of fuel atomization areas through individual atomizers and its quality, as well as the distribution of the mass ratio of fuel components across the cross-section of the chamber. TPU pump testing to evaluate pump design during prototyping, determining head pressure, capacity, cavitation and efficiency characteristics used to control the parameters and quality of manufactured pumps and the engine settings. As a rule, water is used as the operating fluid. TPU turbines are tested both with research purposes and to determine the actual characteristics of the manufactured turbines. They are essential for calculating engine setting parameters. Autonomous turbine tests can be carried out with natural gas, but more often model working fluids such as air or other gases like freon are used. When checking and testing the control and regulation system units, testing operation within a specified life cycle or number of switching operations, determining and adjusting their regulation characteristics, and studying the effects of various external factors on the operation are carried out. These tests can be conducted both with natural and model working fluids. For example, liquid nitrogen can be used instead of liquid oxygen, which considerably simplifies the testing technology, since the risk of explosion or fire is excluded. Strength tests of engine components. These are static tests of closed volumes, housing parts of pumps and turbines, combustion chamber cooling ducts, etc. are carried out by hydropressing method at pressure 1.25 to 1.5 times greater than the working pressure. If necessary, tests are conducted up to the destruction of the tested construction. Dynamic tests. Pump impellers and turbine discs are dynamically tested on special benches at elevated rotor speeds. Fuel lines, pump housings and injector head cavities are tested for the effects of hydraulic shocks. Vibration tests are carried out on vibration benches to determine the natural frequency and shape of natural vibrations by establishing resonance frequencies. Based on the results of strength tests, weaknesses are identified and decisions are made concerning structural modifications or changes in production technology. Comprehensive verifications of electrical and automation systems, which include remote control of electrical circuits of pyra, electro and pneumo valves, sensors, actuators, etc. The test programs are used to check the functioning of the automation components by activating the respective actuators. Tests of the entire fuel feed system of the LPRE together with the automation system. In these tests, the operation of the fuel supply and engine regulation of the supply of components to the combustion chamber and accordingly combustion there is tested. The effect of the combustion chamber is simulated by installing throttling devices at the outlet of the fuel and oxidizer pressure lines. The throttling devices shall be selected so that the required pressures of the fuel components at the combustion chamber inlet and their mass flow rates equivalent to those in full-scale operation are ensured. Such tests allow the fuel supply and control system to be debugged safely and without the possibility of damaging the combustion chamber during the tests. The operation process of a chemical fuel-powered LPRE involves the combustion or decomposition of fuel, which produces large amounts of heat. The resulting thermal and dynamic loads have a major impact on the engine's working process and the performance of its component. All this has to be simulated in a test. There is only one way to do this, by running the engine. At the same time, the use of high-performance and often aggressive and toxic components in liquid rocket engines makes the testing process dangerous and expensive. Fire tests are carried out on the hot parts of the LPRE, the combustion chamber and the gas generator, as well as the entire engine. For the combustion chamber and the gas generator, autonomous fire tests can be carried out. These are usually conducted on special benches equipped with a fuel expulsion system. Such test benches provide a considerable amount of information. In these tests, combustion processes are analyzed, combustion stability is achieved, cooling modes is assessed, and the energy values are updated. The uniformity of the temperature field in a gas generator plays an important role. It should be noted, however, that for high thrust engines with a high pressure in the combustion chamber, the creation of such test benches can be very expensive. The main type of firing test is the assembly test of a liquid rocket engine. Only this type of test can give maximum information on the performance of the LPRE and its actual characteristics. During these tests, each unit works under real conditions, similar to operating conditions, and the mutual influence of the units on each other is automatically taken into account. When performing fire tests, start-up and shut-down cycles are selected. The actual characteristics of the LPRE and their stability during the specified life cycle are determined, and the LPRE's reliability and performance during operation in the propulsion system are assessed. During firing tests, the LPRE operates in both steady and transient modes. In steady modes, the LPRE parameters are kept virtually constant over time. The steady modes include the main, pre-start and last stages of thrust change. Transient or unsteady modes are modes in which the LPRE parameters change over time. These include starting, switching modes, automatic regulation and shutdown of the LPRE. Engine operation is tested under various combinations of external and internal factors during the firing test. External factors are defined as physical effects on the operating mode of the LPRE caused by external conditions. These include changes in pressure of fuel components before the pumps, changes in the fuel density due to the changes in fuel temperature grade, changes in the proposition of thrust regulators and fuel component ratios caused under operating conditions by controlling actions from the rocket or spacecraft control system. Internal factors are commonly identified as physical effects on the operating mode of the LPRE, which are caused by the specifics of the construction process. They arise due to deviations within manufacturing tolerances in the dimensions or shapes of parts, which ultimately lead to a variation in the characteristics of the units. A liquid propellant rocket engine works under specific conditions on the ground, during flight through the atmosphere and in space. And it is only possible to check all the necessary parameters in flight. However, this requires very high costs to build a flying laboratory, measuring instruments, data transmission systems, etc. Also, performing flight tests for imperfect, newly built engines is dangerous, with a high probability of accident, and then all the costs incurred would be lost without effect. For this reason, much of the testing is done on the ground. They will allow some of their components to be refined before the flight test, and thus reduce the probability of failure, as well as significantly cut the costs of the LPRE development. Ground testing refers to the testing of a product and its assemblies under terrestrial conditions, while flight testing refers to the testing of a product and its assemblies in a transportable vehicle under realistic operating conditions to confirm their performance and determine their suitability for their intended use. However, with all the advantages of flight tests, they have the following disadvantages. Flight tests are very expensive, and their cost will increase dramatically due to launch failures when not sufficiently reliable LPREs are tested. Flight tests have less information than ground tests because of the limited number of measurement instruments and telemetry channels. Flight tests may allow for significantly less variation in factors affecting the physical process of the LPRE during testing. In normal bench tests, it's not possible to create performance-like conditions in all cases. This is particularly true for LRFs of rocket upper stages and spacecraft. In order to achieve high performance in ground-based testing, the goal is to simulate real operating conditions as much as possible and to take into account the influence of all operating factors. For this purpose, facilities are created to ensure maximum similarity of the real conditions with respect to the main influence factors. During ground testing, the following tasks are carried out. creating loads in the testing process to assess the performance of the design elements or to identify weaknesses in the design, determining the performance of a specific component or of the LPRE as a whole. Tests may cover one or both of these objectives. For the first task, tests can be conducted in weighted modes to identify all possible faults and failures earlier. The wide variety of requirements for ground testing results in the need for a large number of test benches for unit-by-unit testing and testing of assemblies and of the LPRE as a whole. For ground testing of LPRE of upper rocket stages, high altitude conditions simulating the launch and shutdown of the LPRE, as well as a continuous gas flow in the nozzle, are achieved by using pressure chambers or vacuum units equipped with ejectors and outlet diffusers. Since the operating mode and performance of the LPRE can also be significantly affected by the temperature of the fuel components and its design, in some cases, thermo-vacuum tests are carried out on specially designed test benches for this purpose. The combined operation of the propulsion system and the LPRE is verified by comprehensive ground tests as part of the rocket stage. Intensive ground testing of the LPRE and extensive use of real-world simulation facilities significantly reduce the amount of expensive flight testing. Flight testing is the testing of a product and its components as part of a moving vehicle under realistic operating conditions. Although flight tests are less informative than ground tests, due to the limited number of measuring instruments and telemetry channels, as well as their high cost, verification of joint operation of all elements and systems of a liquid propellant rocket engine and flying vehicle under operation conditions is obligatory. Flight tests of a newly developed or modified LPRE conducted to check its performance against technical requirements, during which additional development of the LPRE can be carried out, are called flight design tests. Flight design procedures and their scope can vary significantly. They depend on a number of factors, most importantly the purpose of the test engine and the cost of the flight test. For example, flight design tests of LPREs for relatively small unmanned flying vehicles may be initiated early in the program development phase to identify design weaknesses. In the case of heavy lift rocket systems, and especially for manned aircraft, flight tests are only conducted in the last stage of development of the LPRE when it has a sufficiently high reliability. If the flight design tests performed are not of high quality, then state flight tests are provided, which are the final stage of verification of the developed LPRE. However, the final flight tests must necessarily be performed on the rocket for which the engine is being developed. Research tests. The current state of theory and experience in the design of the LPREs doesn't allow the development of a new engine that differs from the previous ones in scheme of principle of operation, structural materials of fuels, higher mechanical and thermal loads, and higher parameters without preliminary experimental studies. As a rule, the design of an advanced liquid propellant rocket engine is based on the result of preliminary R&D, a significant part of which requires special research tests. The main purpose of R&D testing is to contribute to the creation of the scientific and technological groundwork necessary for the further development and improvement of liquid propellant rocket engines. Research and development tests are conducted at research institutes, design bureaus, and laboratories of universities. R&D tests are conducted both on LPRE and on individual components. The results of R&D help explain individual phenomena, clarify and supplement existing theories, and sometimes create new ones. They are used in the preparation of a justified design of a new LPRE scheme, which reduces the amount of development work. Research studies are expensive and not always convenient, so they are replaced by model tests. Simulation allows to significantly reduce the power that is expended on the experiment, to reduce costs for construction of benches and experimental equipment, to conduct the experiment under more comfortable conditions, at acceptable temperatures and pressures, etc. To replace toxic and explosive working fluids with safe and harmless ones. To adapt the model specially for the purpose of the experiment. The main requirement for R&D test facilities is that they should be as flexible as possible, so that different objects of the same class can be studied, a variety of measurements can be taken, and the effects of certain influences or phenomena on the characteristics of an object can be separated from others. During the development work on a new liquid propellant rocket engine, a set of development tests are carried out, including certain types of tests. Research tests, preliminary tests, acceptance tests. The necessity, composition and sequence of tests during development work shall be established by the developer of the LPRE, taking into account the requirements existing in the industry. The entire scope of testing during development work is carried out in accordance with a comprehensive program of experimental testing of a liquid propellant rocket engine, which is designed so that the required technical parameters and reliability of the new liquid propellant rocket engine are achieved in the minimum time and with minimum cost. Unlike research and development tests are carried out only on actual constructions of a unit under development or a liquid propellant rocket engine as a whole. In the research phase, comparative refinement and development tests are carried out. The purpose of comparative tests is to accept the best initial variant of LPRE design for further refinement. Refinement tests are tests for preliminary verification of results on performance parameters of liquid propellant rocket engine and determination of possibility of fulfillment of technical specification for liquid propellant rocket engine under development. The purpose of refinement tests is to refine the design of liquid propellant rocket engine components and the engine as a whole to meet its performance specifications, which is achieved by identifying and eliminating factors that degrade performance and reduce the performance parameter reserves of the liquid propellant rocket engine. The following tasks are solved during developmental testing. Refinement of the LPRE component design and the verification of the correct choice of materials and technology for manufacturing parts to ensure durability and reliability. Fine-tuning the performance of the liquid propellant rocket engine and its control system to the level specified in the technical specification. Testing of performance characteristics of the liquid propellant rocket engine and its protection systems under the impact of various external and internal factors. In the process of developmental testing of liquid propellant rocket engines, there is a continuous search for limiting structural and functional elements with minimum reliability, development of measures to improve their reliability to the level of requirements of technical specifications, and the subsequent verification of the effectiveness of these measures. The comprehensive program of experimental development provides for an advanced and as complete as possible autonomous tests, which are completed by verification of compliance with all the requirements, including reliability of specific technical specifications for a specific element of a liquid propellant rocket engine design. Since only 40 to 50% of all design and technological defects are revealed in the process of autonomous tests, it is necessary to conduct developmental tests of full-size liquid propellant rocket engines. In addition, the actual characteristics of liquid propellant rocket engine, primarily thrust, specific thrust impulse, and reliability can be assessed only based on the result of its tests. The full-size liquid propellant rocket engine development tests are also necessary for final testing of the combustion chamber and gas generator, as a result of which the parameters of the turbopump unit are also refined and the design of the unit is improved. The work to ensure a reliable launch of a newly built liquid propellant rocket engine, including at high altitude, and its shutdown to ensure the safety of the liquid propellant rocket engine after shutdown and the specified value of the LPRE after effect pulse are extremely important and complex. To test the effects of weightlessness on the launch process, flying laboratories based on specially equipped aircraft are used. For multiple-use liquid propellant rocket engines, the scope of tests for testing and verification of reliable operation of ignition systems and automatics designed for multiple actuation is increased. Methods of control of technical condition of LPRE after firing starts, cleaning of LPRE from residual fuel components, and preparation for long-term storage are also practiced. Once the required strength characteristics of the elements have been obtained, the developmental firing test phase of the full-size liquid propellant rocket engine begins. Tests are conducted with a gradual increase in thrust level and operating time. After the nominal performance is achieved, tests are conducted for the service life specified in the technical specifications for the development of the rocket engine, with changes in the conditions for the pressure in the chamber and the ratio of fuel components corresponding to the operating conditions on the rocket. Since a large number of external and internal factors have a significant influence on the level of parameters and the degree of loading of the LPRE elements, tests should also be conducted to verify their influence. The types of factors, their combinations and levels are selected so as to create the most stressful but practically feasible operating conditions for each of the main elements of the liquid propellant rocket engine. External factors are simulated by bench test systems. The influence of internal factors on the output parameters of the LPRE, thrust and fuel component ratio, is compensated by appropriate adjustment. However, this doesn't eliminate the dispersion of the internal parameters, pressures behind the pumps, gas temperature before the turbine, etc. And under certain operating conditions, they can become critical. To eliminate the influence of uncontrolled random and tolerance variations in setting accuracy, which might lead to failure to reach the target level of the parameter under test, tests are carried out with values of external factors exceeding those specified in the technical specification. This excess may be up to 15% or more of the nominal level. To identify design weaknesses associated with accidental failures, not only are resource tests conducted at the modes established by the technical specification, but the following methods of searching for the limiting structural and functional elements of the LPRE are now widely used. During test preparation or when tests are conducted, values of factors whose effect is being investigated are set above normal operational limits. The tests shall be conducted until a failure or until the appearance of an emergency protection signal indicating loss of performance or the appearance of a critical defect preventing further normal operation of the LPRE. Tests are performed up to a certain limit of change in factors. At the same time, tests are conducted for a period of time longer than that specified in the technical specification. The same liquid propellant rocket engine is repeatedly tested, thus increasing the operating time and the number of cycles for each of the liquid propellant rocket engines, and the operation modes are made heavier. The latter is achieved during accelerated boost tests by special tuning of liquid propellant rocket engine to the limit values of main parameters by wide variation of operation modes with appropriate regulating elements. In a number of cases, complex weighting of tests is conducted simultaneously on parameters, duration of operation, and number of switchings. The limit values of parameters of the weighted modes of liquid propellant rocket engine must not exceed the values at which the physical picture of the process under study changes. In the process of developmental testing, the performance of the liquid propellant rocket engine under some emergency situations is also investigated. For certain types of liquid propellant rocket engines, such as spacecraft propulsion correction systems, accelerated abbreviated tests may be necessary. In this case, the operating conditions are tightened, making it possible to shorten the test time. Such systems typically operate in cyclic mode. With accelerated tests, the pause time can be eliminated and the operating time shortened. In operation, the level of basic parameters is set higher than in operation, while the number of cycles remains unchanged. After the developmental testing phase, of which the developmental testing is main part, the pre-testing phase commences. During the pre-testing phase, final development and flight tests are conducted. The purpose of the final development tests is to confirm that the performance of the liquid propellant rocket engine, including its reliability, complies with the technical specification and to evaluate the possibility of submitting it for acceptance testing. The basic material for assessing reliability is the result of final inspection tests. Tests similar to final refinement tests are sometimes also called qualifications. Reliability can be evaluated from the results of all tests performed on an LPRE that has a final design of the main elements. At the same time, a significant number of tests are required to quantify the reliability of a liquid propellant rocket engine. Time and cost savings can be achieved by performing multiple tests on a limited number of liquid propellant rocket engines, increasing their continuous operation time and weighting the modes. The methodology of the final development tests is very similar to that of the weighted mode development tests and the adverse combination of external and internal factors tests. At the final stage of final development tests, when the confirmed reliability level of the developed LPRE is sufficiently high, bench tests of the LPRE as part of the propulsion system are conducted. The main purpose of these tests is to provide a preliminary assessment of the performance of the liquid propellant rocket engine as part of the propulsion system. At the same time, the effects of the liquid propellant rocket engine on the propulsion system performance are examined. If several liquid propellant rocket engines are installed in the rocket stage, their mutual influence and their impact on the performance of the stage are assessed. Propulsion system tests are conducted mostly in terrestrial conditions. In some cases, where the propulsion system parameter level allows to the use of high-altitude test benches, tests are conducted under simulated operating conditions. During bench tests of liquid propellant rocket engines in the propulsion unit, the launch and shutdown of the liquid propellant rocket engine under pressure failures and water shocks in the standard lines of fuel component supply are checked if it's necessary, finalized. The performance of the liquid propellant rocket engine during the service life with standard system of tank charging and fuel components extraction for rocket needs under full-scale vibration loads and thermal design mode is assessed. The bottom pressure level in launch conditions, value and dispersion of pulse after. Flight and development testing of prototype LPREs is usually carried out after successful completion of bench tests as part of the engine unit. The main purpose of flight development testing is to verify and confirm the performance of the LPRE and to check its performance against the specifications under actual operating conditions. In the course of flight and development testing, additional modifications can be made to the liquid propellant rocket engine. A final conclusion about the performance of the LPRE under actual operating conditions can only be made based on the result of flight tests as part of the rocket system for which it was designed. The flight development tests shall be carried out according to a program agreed with all the organizations concerned. When developing the methodology for processing and analyzing test results, special attention shall be paid to the adequacy of the selected scope of parameters to be measured and the accuracy of their measurement. The information obtained during flight tests shall first be subjected to operational and then full analysis. A small number of parameters that most closely characterize the performance of the rocket engine is selected for operational analysis. It is checked whether it was functioning normally and what noticeable abnormalities occurred during its operation. A full analysis is performed after decoding and assessing the reliability of the telemetry information. As a result, the main characteristics of the LPRE and transient mode parameters are determined, including startup and shutdown, actual vibration overloads in individual points of the LPRE, and the level of the pressure pulsations in the fuel lines, thermal characteristics of design elements in various operating modes. Tuning accuracy is assessed. The main manifestation of any malfunction in the LPRE is accompanied by a transient process and parameter changes. Analytical and experimental methods are used to determine the cause of faults. When necessary, simulated faults are simulated under bench conditions before a final conclusion on the cause of the anomaly is reached. The analogy in changes of parameters in flight and bench tests is an additional proof of the correctness of the accepted version. A conclusion on the completion of the test tasks is made for each launch. On the basis of the information obtained, the necessary modifications are made to the liquid propellant rocket engine, and the tasks and programs of the subsequent test are adjusted accordingly. The main criteria for completing the entire scope of flight and development testing may include refinement of the main parameters and characteristics of the liquid propellant rocket engine, confirmation of its performance characteristics, confirmation and clarification of the achieved level of reliability. Successful completion of final development and flight design tests is the basis for submitting the LPRE for acceptance testing. Acceptance tests include interinstitutional and state flight tests. The interinstitutional tests shall confirm that the main technical characteristics of the LPRE meet the requirements of the technical specification and demonstrate the availability of its performance reserves, as well as establish a reference standard for the LPRE for serial production. Interinstitutional tests are carried out by a commission consisting of representatives of several interested organizations, the program of which is agreed with the representatives of the organizations concerned and approved by their management. This includes the carrying out of resource and special tests for external influences. A series of special tests shall also be carried out prior to the interinstitutional tests. Transport tests to confirm the performance of the LPRE after it has been transported by vehicles over specified distances. Climatic tests after long-term storage under extreme temperature and humidity conditions, etc. The Interinstitutional Test Committee reviews all documentation, development history, results of all tests and other materials prior to testing. Based on its review of these documents, it issues an opinion on the approval of the LPRE for testing. After the tests, the liquid propellant rocket engine is disassembled and its components are defective. The committee's work is completed by drawing up an act on the interinstitutional tests. Their successful completion is the basis for recommending that the LPRE be put into series production. Technical documentation corresponding to the LPRE that passed the interinstitutional tests is standardized. In some cases, interinstitutional tests of the LPRE are combined with institutional tests of the propulsion system. State flight tests are conducted to confirm that the characteristics and performance parameters of the LPRE meet the requirements of the technical specifications under actual conditions of its use and to make a decision on the possibility of introducing the LPRE into service. The tests of a liquid propellant rocket engine at the manufacturing plant during its serial production and in operation belong to the group of engine performance tests. During series production, a number of assemblies and units of the LPRE are subjected to various types of control and development tests, mostly cold tests, similar to those performed during development work, but they are carried out according to standard simplified programs. Assembled LPREs are subjected to tests to verify the quality of their manufacture and assembly, their compliance with the main indicators with the declared parameters, as well as to check their reliability. After completion of preparations for serial production of a new LPRE or resumption of production of a previously manufactured LPRE, in-service tests are performed. The in-series tests are performed both on individual assemblies and on a complete LPRE. The purpose of the installation tests is to show that the series-produced liquid propellant rocket engine conforms in terms of reliability and performance to the technical specification and the reference, since the technological process of producing a series-produced LPRE always differs from the process of producing it in the prototype production. The applied methods of control of commercially produced liquid propellant rocket engines largely depend on their purpose and design features, the fuel components used, etc. The main types of test currently used to control the quality of commercially produced liquid propellant rocket engines are the following: control technological and confirmatory periodic or control sampling tests. The control and technological tests are fire tests to which each fabricated LPRE is subjected. Their purpose is to control the quality of fabrication and assembly of a specific LPRE, verify its performance, its compliance with the requirements set forth in the design documentation, and the possibility of submitting the LPRE for operation or other tests. If the LPRE is disassembled after control and technological tests, its defect analysis is an additional means of control, which makes it possible to identify latent and undeveloped defects. Based on the result of the control and technological tests, the LPRE is also adjusted to the specified mode of operation if necessary. The duration of control technological tests is usually a few tenths of seconds. During these tests, the engine can be operated in several modes in terms of combustion chamber pressure and fuel component ratios. The duration of operation in each mode shall not be shorter than the time required to change and stabilize the thermal, vibration and other types of loads on the LPRE components. For example, the time for stabilization of parameters of a liquid propellant rocket engine after launch is approximately 5 to 20 seconds. Usually, to ensure correct determination of the main parameters in steady-state modes, a delay of at least 10 seconds is made. The number of parameters to be measured in series testing is significantly lower than in development testing. Usually, they are limited to measuring the parameters required to determine the basic data of the LPRE. A liquid propellant rocket engine is considered to have passed the performance test if its program is fully completed, the parameters to be controlled are within the specified tolerances, and the elements of the engine have no defects preventing its further operation. The purpose of the confirmatory periodic tests is to check the quality of the production of the LPRE and to verify its performance and operability parameters comply with the requirements set on the restatements of work. These tests are carried out after a certain period of time. Sample testing has the same purpose but involves the testing of one or more LPREs from a given batch. Confirmatory periodic tests are long-term tests of liquid propellant rocket engine conducted for a resource or for a time exceeding it, in the course of which its operation modes are changed within the whole operational range. If the technology of testing of certain LPREs provides for control technological tests, LPRE, which has previously passed control technological tests, shall be selected for confirmatory periodic control sample tests. Based on the result of the confirmatory periodic tests, the main parameters of the LPRE are determined and their change over the service life is assessed. After these tests, the liquid propellant rocket engines are disassembled, flowed, metallurgically examined, and subjected to other types of control to establish their technical condition. If the performance of the LPRE and the condition of its components meet the specifications, the production plant shall be entitled to ship the remaining LPRE manufactured during the reporting period to the customer. Special periodic tests are intended to periodically determine whether the performance and warranty serviceability reserves of the LPRE are at the level achieved at the completion of the DW. In addition, these tests are used to check the stability of the technological process. Special periodic tests are conducted in an extended range of parameters relative to the operating range in order to verify the stability of production. Type tests are carried out to determine the effect of various technological and design measures carried out on an engine in series production on its performance and operability. Comprehensive testing of commercially available liquid propellant rocket engines is most often carried out by one of the following methods. Control and technological tests with subsequent reassembly, plus confirmatory periodic tests, control and sample. Control and technological tests without subsequent reassembly, plus confirmatory periodic tests, check and sample. Cold process control tests, plus confirmatory periodic tests, sample control. Confirmatory periodic tests without preceding inspection and sampling tests, inspection and sampling. The first of these methods allows a complete inspection of the technical condition of all parts by means of inspection and non-destructive testing. These may reveal hidden defects that are not detected by short-term testing. The disadvantage of this method of control is the possibility of poor quality assembly after the inspection and testing. In addition, there are a significant number of single-use parts, seals, fasteners, etc. in any LPRE, the technical condition of which is not checked during the process control tests. This disadvantage is eliminated by the second method. However, in this case, additional requirements are imposed on the design of the LPRE and its post-test proceeding methods. The LPRE must be capable of multiple burns even if it is intended for single use. This requires the complication of engine components. The disadvantage of testing without reassembly is also the difficulty of detecting hidden defects. In this regard, the requirements to methods and means of technical diagnostics for testing and subsequent examination of the condition of the assemblies and units by methods of non-destructive testing are increased. Some liquid propellant rocket engines are subjected to a cold process control test without subsequent reassembly. The basis of this test is cold flow tests with simulated propellant, oxidizer and working fluid. The simulated liquids and gases must not react chemically with the structural materials and must be easily removed. The cold process control tests allow to verify the correct assembly and make sure that there are no foreign bodies in the line of the liquid propellant engine. Check the operation and evaluate the performance of pumps, turbines, valves and control system elements. Determine the accuracy of the LPRE tuning in terms of fuel component ratios. A significant disadvantage of these tests is that there is no testing of the LPRE under real operating conditions. In some cases, process control tests are not performed and product quality control is carried out only by confirmatory periodic tests. Such a method may be considered appropriate when the effects of fuel components on the structural components of a test and the subsequent prolonged storage of LPRE lead to a reduction in its reliability. However, with this method, the period set for confirmatory periodic testing or the batch size from which the LPRE is selected for sample testing will usually be shorter than when pre-process testing is provided for. Reusable liquid propellant rocket engines, which are used in reusable space transportation systems and rocket stages, need to be monitored periodically. For this reason, methodologies are being developed for monitoring the technical condition and preparation for the next flight. These procedures are based on inter-flight firing tests. Tests of reusable liquid propellant rocket engines during the inter-flight period belong to the in-service group and include inter-flight technology validation tests, inter-flight confirmatory tests. Inter-flight technology validation tests are performed on each LPRE immediately after the flight or necessary remedial work is performed. As a result of these tests, information on the technical condition of the liquid propellant rocket engine should be obtained, which allows the conclusion to be made on its compliance with the design documentation. The operating time for the in-flight technology validation test is limited to the time necessary to obtain the required amount of information. However, in-flight technology validation tests do not guarantee trouble-free operation of reusable rocket systems whose operation is just beginning, so in-flight confirmation tests are provided for. One of the previously operated LPREs that have passed the in-flight technology validation test is selected for in-flight validation testing. It is subjected to tests or warranty operating time. The size of the batch is specified in the design documentation. If the in-flight confirmatory tests are successfully completed, permission will be granted to use this batch of liquid propellant rocket engines again for the intended purpose. As statistics accumulate on the flight operation of a particular reusable space transportation system, the methodology for inter-flight control of LPREs can be simplified. I would like to conclude today's lecture with this. In this video, you have learned what are LPRE tests and what are they for, what types of tests there are and when they are conducted, the main advantages and disadvantages of different types of tests. I hope you found this lecture understandable. If you do have any questions, comments or errors, don't hesitate to let us know in the comments or private messages. We will meet you in the next video lecture.